Welcome to This Explainer. Today, we're taking a look at the hidden, high-stakes trade-offs of hardware engineering. You know, every sleek device we own actually hides this secret world where mechanical and electrical demands are just in a constant tug-of-war. Let's get right into it. Here's a serious question for you. How do you build a circuit board that folds 200,000 times? Think about the modern electronics right there in your pocket. We demand screens that bend, that fold, twist, you name it, but underneath that screen is a printed circuit board. And traditionally, that's a rigid, pretty brittle piece of fiberglass. So how on earth do you build one that can survive being folded over and over again? To put that crazy number into perspective for a second, surviving 200,000 folds is basically the equivalent of opening and closing a phone 100 times a day, every single day, for over 5 years. Achieving that kind of extreme dynamic folding without a single electrical failure, that requires an absolute mastery of both physics and chemistry. To understand exactly how engineers pull this off, here's our roadmap for today. We'll look at the flexible electronics revolution, choosing the surface finish, the mechanics of bending, designing for foldable phones, high-speed signal integrity, and wrap up with shielding and rigid flex transitions. Starting with Section 1, the flexible electronics revolution and pushing the limits of modern devices. This is really where our journey begins, right at the intersection of consumer demand and stark engineering reality. The core truth of flexible printed circuit boards, or flex PCBs, is that they are a constant push and pull between physical durability and electrical performance. Every single choice in hardware design has a consequence, right? If you optimize for mechanical flexibility, well, you might just sacrifice your high-speed electrical signal. But if you prioritize electrical perfection, your board might literally snap in half when you bend it. Let's see how this plays out in the real world. Moving on to Section 2, choosing the surface finish, the chemistry of reliability. This is the very first major trade-off engineers face, picking the right chemical finish to protect the copper traces on the board. And it's a pretty stark contrast. On one side, we've got ENIG, which stands for Electroless Nickel Immersion Gold. It gives us that reliable gold surface we all trust. The nickel barrier underneath creates amazing corrosion resistance. I mean, these boards can survive harsh industrial environments for over 5 years. But it's expensive. And worse for our purposes, the nickel can actually cause brittleness in dynamic flex applications. On the flip side, we have OSP, or Organic Solderability Preservatives. This stuff practically disappears on the board, maintaining incredible copper integrity when you bend it. Plus, it's like 50 to 70% cheaper, which is huge. But its absolute kryptonite is the environment. Prioritizing the massive cost savings of OSP without thinking about environmental factors like humidity can lead to absolute disaster. Just listen to this warning from an industry expert.
I once had OSP boards stored in humid conditions that oxidized beyond repair in months.
Yeah, all those upfront savings, they immediately evaporate into massive warranty claims. Which brings us to Section 3, the mechanics of bending and finding the breaking point. When you bend a flex circuit, the inside of the bend faces compressive forces, while the outside faces tensile forces trying to pull it apart. If you bend it too tight, you will literally tear the board in half. So engineers have to define the limits using what's called the minimum bending radius. This is simply the minimum degree to which a flexible circuit can be bent without sustaining damage. A smaller bending radius equals greater flexibility, but you can't just guess this number. Engineers have to calculate it meticulously. Let's demystify the engineering math a bit. There are these golden rules of thumb for bending ratios. Notice the massive difference between a stable design, which is basically bent once during installation and left alone, and a dynamic design that bends repeatedly. For a single-layer dynamic board, the ratio is 100 to 1, but for a double layer, it jumps to 150 to 1. And look at multi-layer dynamic designs. They simply aren't recommended at all because they're just too thick to survive constant folding. Let's ground this math with a specific example. The formula is the R/H ratio multiplied by the application's thickness. So if we take our dynamic double-layer ratio of 150 to 1 and multiply it by a board thickness of, say, 190 micrometers, we get a minimum bending radius of exactly 29 millimeters. If an engineer tries to bend that board even a fraction tighter than 29 millimeters, it's going to fail. It's actually amazing how knowing this one simple calculation saves millions of dollars in broken hardware. Next up, Section 4, Designing for Foldable Phones, the 1.5 millimeter challenge. Now that we understand the standard math, let's look at what happens when these rules are pushed to the absolute extreme. Remember our 29mm example? Well, flagship foldable phones require a bend radius as tight as 1.5 millimeters. It's completely wild. To eliminate bulk and conquer that fold fatigue over hundreds of thousands of cycles, engineers have to get incredibly innovative. They use ultra-thin total thicknesses. We're talking between 0.08 and 0.15 millimeters. They drop traditional adhesives entirely, opting for adhesiveless polyamide instead. They use rolled annulled copper because its green structure resists flex fatigue way better than standard electrodeposited copper. And, super importantly, they strictly keep vias, the tiny holes that connect layers, out of the fold zone entirely to avoid stress concentration. All right, Section 5, high-speed signal integrity, moving data at 10 gigabits per second. So here is a major plot twist in our balancing act. Making the board thin enough to fold is really only half the battle. You also have to make sure that high-resolution data moving at up to 10 gigabits per second actually survives the journey. As noted in this Glenair white paper, pushing 10 gigabit speeds demands extremely strict impedance matching. Any physical change in the board, a bend, a transition, a change in trace width, can cause impedance discontinuities, and those distort the signal and cause data errors. To combat this, engineers rely on a very specific toolkit. They utilize controlled impedance traces with incredibly precise geometry. They carefully select low-loss dielectric materials, because if you use a material with high insertion loss, it acts like a sponge, just absorbing and dissipating the signal energy as heat. They also employ matched terminations, like series resistors, to absorb reflected energy and stop signals from bouncing backward. And finally, they meticulously control layer-to-layer spacing to perfectly balance signal integrity with mechanical flexibility. Now for our final section, Section 6, shielding and rigid flex transitions, the terrain metaphor. This is where mechanical and electrical demands clash the hardest. Take electromagnetic interference, or EMI shielding, for example. You could use crosshatch shielding. It's a mesh-like pattern that is wonderfully flexible and lightweight, but it's less effective at blocking lower-frequency EMI. Or you could use continuous copper sheet ground planes. These offer incredible EMI protection and structural strength, but they're rigid, which severely limits how much the board can actually bend. It's a classic, agonizing trade-off. You'll find many devices use boards that have both rigid and flexible sections. But changing from rigid fiberglass, like FR4, to flexible polyamide involves a sudden change in the material's dielectric constant. Essentially, it's a shift in how the material interacts with electric fields. For an electrical signal moving at high speeds, this is exactly like a high-speed train suddenly hitting a change in track gauge. If you don't manage it perfectly, your signal just derails. To keep that signal safely on the tracks, engineers use tapered traces to make physical transitions as gradual as possible. They try their best to match the dielectric properties between the two substrates, they use controlled impedance routing, and critically, they have to ensure uninterrupted return paths at the board mount connectors. Because a single break or gap in the return path at the connector interface, that can cause massive signal reflections and crosstalk. So what's the big takeaway from all this? Well, whether an engineer is agonizing over ENIG versus OSP surface finishes, or calculating a 1.5 millimeter bend radius to stop a phone from snapping, or desperately trying to match impedance across totally different materials, successful hardware design is just a constant, brilliant balancing act. The perfect device isn't actually the one with zero compromises. It's a masterpiece of meticulously managed trade-offs. Which leaves us with this final thought. We are already folding screens in half and pushing 10 gigabit speeds through fractions of a millimeter. As our data demands continue to skyrocket, and as we all demand even thinner, more dynamic devices, what impossible trade-offs will hardware engineers have to balance next? Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll see you next time.